Hello, this is my Circuits and Capacitors lab. This presentation will be split into 5 sections: an introduction, a procedure, a section on series circuits, a section on RC circuits, and finally a conclusion. So in this lab, we were asked to build on our knowledge of circuits by modeling circuits using a third-party software application called the Circuit Construction Kit. And we use this to model both the charge and energy conservation in series circuits and also RC circuits and time-dependent voltage. We've also used linear regression to determine the time constant or the RC value of the circuit experimentally. The fundamental physical principles involved are Ohm's law, the node rule, and the loop rule shown here. Finally, for results, we found that the RC value or the time constant was 6 seconds. So now for the procedure. As I stated, I used the Circuit Construction Kit application to build and test circuits using the drag and drop features. I used this application to build 2 different circuits, a series circuit and an RC circuit. I also used the voltmeter to measure potential difference or voltage and the ammeter to measure current. Finally, I used the stopwatch to gather potential difference or voltage versus time data to find RC. Now for the series circuit. For quantitative observations for this circuit, I have the following table. So the current through ammeter 1 and ammeter 2 were the same, of 0.02 amps, and even when ammeter 2 was inserted backwards, the current was the same. When ammeter 2 was disconnected, however, the current in ammeter 1 was 0 amps, and also in this case, the voltage between the two loose ends of the circuit was 3 volts. This table shows the voltage across each of the elements of the circuit corresponding to the diagram shown on the bottom left. The diagram or the graph in the bottom right shows graphs the voltage versus the component, and notice that the net voltage through a loop of the circuit is 0 volts. So now for results, as I said, when the circuit is broken, there's no current through the circuit. However, the voltmeter's reading is 3 volts, which is equal to the voltage of the battery. Also, as I said, the sum of the components, the sum of the voltages across each of the components is 0 volts, and this is due to the loop rule. Also, there's no change in the current when the voltmeter is added because the voltmeter is ideal and has infinite resistance. Finally, when you replace the voltmeter, if you replace the voltmeter with an ammeter in parallel with the 100 ohm resistor, ammeter 1's reading increases to 6 amps. And this is because there's no current going through the 100 ohm resistor because it is in parallel with a 0 ohm ideal ammeter. And finally, we have the calculations for the resistance of each of the resistors, the wire, and the ammeter based on Ohm's law. Now onto RC circuits. So I found that when the battery, the 10 ohm bulb, and the capacitor are in series, the bulb begins to light up and then slowly dims, and the current decreases to 0 amps. And this is because the capacitor is charging. However, when the 10 ohm bulb and the capacitor are the only elements in series, the bulb also lights up and slowly dims. However, the current reverses direction and the current decreases to 0. In this case, the capacitor is discharging. Now for quantitative observations. So in the top table, we display the time takes to charge and discharge the capacitor in the case of the 10 ohm and 20 ohm bulb. Also, in the second table, we show the relationship between time and the ln of delta V over delta V naught. So now we can plot the data from the previous table to obtain the following graph, which we know is linear. And its slope is simply -1 over RC. So this allows us to solve for the value of RC, which we can find to be 6 seconds. And we can confirm this value of RC with the theoretical value of RC provided by the circuit construction kit, which would simply be the resistance times the capacitance, which we find to be also 6 seconds, confirming our theoretical value. So in conclusion, if we had used an actual ammeter, this ammeter would have some internal resistance that would increase the circuit's total resistance. This would lead to a decrease in current based on Ohm's law. Also, if you compare ideal conditions to the conditions of using a real battery to charge a real capacitor, we can see that in the ideal model for this circuit, the capacitor would charge instantaneously as there's no resistance. However, in the real-world model, the process of charging the capacitor would not be instantaneous, as the capacitor and battery would have some internal resistance, increasing the resistance on the circuit.